Thanks. Yeah, it's great to be here again and to see so many friendly faces and the non-friendly faces. Okay, we'll duke it out. Yeah, so today I'm going to tell you about one of the 3 experiments in my lab at Stanford, and it comes at a good time if you paid attention to the Nobel Prize a few weeks ago. So we're going to be talking about quantum optical spin glasses and the associative memories we can create with them. So this work has been going on in my lab for a dozen years. Started with Alicia Kohler, who's here, raise your hand, yeah. She was one of my first grad students. She's now a professor at JQI Maryland. Also started with Sren Gopal Krishnan, raise your hand. Okay, everybody knows him. He actually started as a grad student as well, working with me on this. His advisor was a real theorist, Paul Gobart. I'm an experimentalist. But yeah, he started as a grad student on this work, and now he's a professor at Princeton. So these are the students who have worked on this, and a postdoc, Ronan Croze, worked on this. He's now a postdoc at MPQ. Brendan Marsh is leading the Associative Memory Project. He's about to graduate and do a postdoc at Gilla. Okay, so good. So let's start with the spin glass. So spin glasses are frustrated magnets. They are found in everyday materials, so if you take magnesium, which is magnetic, and dope it into copper, and you just grow this crystal, you can get one instance of a spin glass, another instance of a spin glass. It's not easy to see the actual spins. You can't. These are just big domains. But these are everyday materials. They can also be very exotic materials, right? So if you look at Cooper superconductors, there's this phase here, the spin glass regime over here, which most of the time you never see on these diagrams because it's like a horrid thing to think about that there's a spin glass down there. But because of disorder, they're always there. And they're in many systems, superconducting qubit systems on the surface, you have spin glasses. They're all over the place. So what kind of defines them, or what is if not defines them, what's a characteristic property? It's this very rugged free energy landscape. So unlike a ferromagnet, which is kind of like, I don't know, Ohio, I'll pick on Ohio, where you have maybe 2 rolling hills and one dip is, all up and one all down. The spin glass looks like the Alps, okay, where you have some villages down here, and they have completely different cultures. They have different dialect, different cheese, different wine, because it's really impossible to visit a neighboring village. The mountains are too high. It's so impossible, actually, that ergodicity is broken. You just cannot, in a thermodynamic system, really explore all these other villages. So what produces this is the phenomenon of geometrical frustration. We heard a little bit about some of these constraints, and this is this particular spin version in this context can be pictured in a triangular plaquette, where if you have an Ising spin, something that either wants to be all up or all down, at each one of these corners, and you have linkages that are ferromagnet between these two, that's blue or plus, and anti-ferromagnetic, where it wants to be opposite, then you can't figure out an optimal way, a unique optimal way of organizing the spin configuration. If you put up here, then you decide to put up here, this is happy, but then you don't know what to do with this vertex, because with respect to here, you'd also want to be up, but then that makes this linkage not happy. So what that means is that you get a proliferation of degenerate states where up or down is equally good, and that leads to kind of landscapes like this. Now, remember, this is just a cartoon. Really, this exists in n-dimensional space. Very, very high dimensional space. So it's kind of hard to picture all the saddle points and stuff like that. Edwards and Anderson, Phil Anderson, Sam Edwards, back in, I think, the 60s, 70s, came up with a simple model for this. It's just an Ising model, but where the Jij matrix is a little bit special. It has kind of random off-diagonal terms that are either positive or negative. If those terms connect any spin to any other spin, this reduces to what's known as the Sherrington-Kirkpatrick, or SK, spin glass, and that's a complete network where everything is connected to everything else, but with a random sign. So some are blue, some are orange, that's positive and negative, connecting the spins. All right? So this spin glass system is very, very deep, not just from a statistical mechanics standpoint, but also kind of points to a wide range of different applications, different communities have thought about this. Phil Anderson in the 90s said that the solution of the problem of the infinite range SK spin glass, that's this all-to-all connected network, really, in the 70s by Parisi, had broad implications for all sorts of fields like neural networks, computer algorithms, evolution, think about how the data from protein folding, or even ecological systems, like how genetic systems evolve over time, and computational complexity. So all of these systems are all NP-complete problems. They all can be reduced to a spin glass, finding the ground state of the spin glass, from things that are kind of abstract, like max cut, traveling salesman, to like everyday things that you might want to do, computer vision, or as academics scheduling classes. The Nobel Prize in 2021 was won for solving the SK model, which was kind of like the first solution of a spin glass model. It ended up being a very bizarre solution, which I'll tell you about in this talk. But because it related to modeling complex systems in general, like climate models, Parisi won with 2 other climate scientists, which is kind of weird, right? But okay, that was really neat. And then, just a few weeks ago, there was another Nobel Prize for spin glasses, in some sense, by particularly John Hopfield. Hopfield's associative memory was kind of the first connection between some statistical mechanics model and some neuromorphic computational capability, something brain-like, via thinking about neural networks. So it kind of connected computer science, stat mech, and neuroscience all together, and that's why he won this. What he showed, and I'll give you a cartoon in a moment, is that if you take the SK model and you give a particular construction of this J matrix, which is the sum over the outer products of a bunch of patterns. So these cassis here are just like zeros and ones or ups and downs that encode some like pattern, like maybe a digitized version of my face, and maybe one of Srang's face and one of Alicia's face. And you add them all together. If you don't add too many of them, then you can actually use this as a memory. And then this led to some notions of neural networks that really capture what we do. Like I haven't seen Alicia in a year or two, and I immediately recognized her this morning because I'm associating her face with my memory. So just to belabor this a little bit, so his paper was in the early 80s. We've come up with Sarang and folks, we've come up with versions of this in quantum optics, and I'll tell you about that in a moment. But to explain like how this works, say you take a really cool pattern and a pattern, and you have a corrupted input. So like these are the ones you stored. Maybe there's 100 of them. And then you want to like do a content addressing memory. So I want to take some pattern that has some errors on it, okay? If the errors aren't too bad, then I should be able, and my brain is doing this right now, should be able to associate this with this pattern and this with that pattern, right? Okay, so the associative memory will do that. Oh, wait, oops. Okay, yeah, it'll do that. and that's success. That's what this thing does. So how do you connect this notion of a brain-like function to a stat mech system? Well, you use this high-dimensional free energy landscape. So you assign the minima of this free energy landscape in high dimensions to some pattern that you're storing. So some like pretty good elements and some really awesome element. Dispersion is the best, by the way. And you put it down here, for those who know me. I'm like, that's a joke. Okay. Anyways, you put it here, and then all of the things that are higher up on the mountainside are errors, right? Those are corrupted versions of that memory pattern. But, if you have a certain type of dynamics, maybe it's Glauber, zero temperature metropolis type dynamics, or maybe it's steepest descent, some dynamics, those dynamics can take you back down here, like a skier coming down the alpine slopes. Okay? If you're like kind of ambiguous, then you might make a mistake. And so that kind of tells you your fidelity of recall. Okay? The number of minima you have is the capacity, and the size of this basin is your recall ability. Okay? So this is what that whole thing means, and it comes from this. I want to kind of just launch into a result, and then I'll tell you how we did it. So this summer, we created the first associative memory with atoms and photons, kind of at the quantum scale, using a new type of cavity QED system that we have. I'll explain all that in a moment. but just to show you some examples of our results, we take we create a network, a spin glass network with a certain JIJ matrix, so a certain realization of this random disordered matrix. We can trap 16 sites at once. So these are not single atoms, like single atom tweezer waves. These are 16 DECs with thousands of atoms per site. So we have 16. We've gone up to like 20, but like this is pretty robust here, 16. And they act as Ising spins. So like orange is spin down and blue is spin up. And they have a random connection between them, up or down. And so we can store a memory, a robust memory, say memory 1, that's this pattern, memory 2 is this pattern, memory 3 is this pattern. We have a capacity of like 12, we have ones that can still store 12 memories in the 16-bit system, okay? But I'm just showing 3 here. And then we can ask, like, if we accidentally flip one of these spins here with like programming in something that like causes it to flip this, does it recall it? Like, can we query it, send light into the system with this flipped, and the light that comes out of the system will be this memory again? It turns out it can with pretty high probability. So these are preliminary recall curves. We actually have better ones. I stupidly didn't put them on the slide yesterday, but okay, we have other ones. So this is like a recall curve, and this is the percent input error. You can imagine this is like the number of bits that are flipped. And you can have this like large basin of attraction. This is proportional to the basin of attraction, like how many bits you can flip. So anyways, we're fleshing all this out now. There'll be a paper on the archive in a few weeks. And one question you can ask is, can you do this with not just a quantum optical system, but a system of like quantum spins as well? It's not just the bosonic field is, single photons, but the atoms are spin 1/2. We think we can. We have a theory paper about this I'll talk about in a moment if I have, at the end if I have time. But this can lead you in a clear direction towards that capability. Mm-hmm.
But if the image is too corrupt, what prevents you to fall into the completely wrong image? So to fit the...
Yeah, you do. That's what sets your recall basin of attraction and eventually your memory capacity. So for Hopfield, so this is another long discussion, and maybe at the end I can get to it. Hopfield, it's basically 0.14 of the number. You can have the number of patterns that you can have for a network of n spins is 0.14 n. Okay, so it's extensive, but like just a fraction of n. Using a spin glass phase and using a driven dissipative system like this quantum optical system I'll tell you in a moment, not only can you get that from 0.14 to actually n, but you actually in principle can get an exponential capacity. And that's because of the driven dissipative dynamics, at least in theory, okay? Yeah?
So why the memory 1 goes to recall probability of 15% at 100% input error?
Yeah, it's just kind of like some noise in the system where like it really should, you just...
I would expect 1/12 or something.
Yeah, yeah, exactly. There's some noise in distinguishing what is a spin up and what is a spin down, just due to noise. We have some more graphs that like get closer down here because we have better signal to noise that don't give us like false errors. That give you some finite overlap. Yeah. Okay. So all right. So that's just like a kind of cool teaser for what we've done, and it comes at like a really good time, I guess, with the snow pole. It's a little bit weird. We've been working on this for like 10 years, and like coincidentally, right when this works, he gets the Nobel for it, but okay, I guess that's good. So let me go back and ask, what is a spin glass phase, like from a real stat mech point of view? How would you describe that magnetic order? Let me just say that, there are very few spin glasses that can actually be solved in some sort of rigorous way. 3D ones, like that copper with manganese, like people don't understand what that order is. Like there's a big fight for like almost 40 years about what the order of that is. So that's an unsolved, one of the great unsolved problems in physics, I think. But the SK model, because of the simplification, it like lives in an infinite dimensional space, or it's mean field. You can think about it either way. You can solve it. That's what Parisi did. And the way you solve it is to recognize that there's 2 order parameters for this. So if you make a phase diagram that is temperature on the y-axis normalized by the width of the spread of the JIJ positives and negatives, and you have on the x-axis like the bias of of the positives versus negatives. So this is like even, like 50-50 positive and negative elements. This is like very much just ferromagnetic. Then you can paint this phase diagram where at high temperatures you have a paramagnet no matter what. That's given by the magnetization. You sum all the spins and normalize it. If you get 0, it's a paramagnet. If you really have all your signs to be all positive or all negative, then you get something that's more or less a ferromagnet, or antiferromagnet. And there you have some, if you, okay, never mind the antiferromagnet, but if you look at the ferromagnet, you get some non-zero magnetization. All right, but then you have this region here where if you have like a roughly equal number of positives and negatives, then you have the spin glass phase. The problem is like, how do you distinguish between the paramagnet and the spin glass? They both have 0 magnetization. But clearly, this thing here, which is rigid, is not the same thing as this thing here, okay, which is fluctuating in time. So you need something else. Before I get to the something else, let me just say that in our experiments, we're not changing temperature so much as we have a transverse field, and we use what's called a superradiant Hopfield-Dickey transition, blah, blah, blah. The point is that this is just a quantum optical way of creating a transverse Ising model. And when we pump light, laser light into the system, we can reach a regime where we go from something that's a paramagnet or a normal phase to a spin glass, which is a superradiant phase. Okay, all right, so what is the second order parameter that we need to distinguish the paramagnet from the spin glass? And that's called the overlap order parameter. And so it looks kind of funky. Let me walk you through that. So it's called, the other name for it is the replica overlap order parameter, because what you do is you take a spin at site I from one copy of the system and multiply it times the spin of site I, the same site, for an exact copy of it from another system. And you label those systems by alpha and beta, okay? And maybe you have a million of these alpha, alpha beta index can go to 1 million. And then you sum over all of those spins, take the time average, and that gives you Q alpha beta. Okay, that seems weird. Like, what the heck is this replica, or this copy? Well, because a spin glass does not self-average, thermodynamic order parameters are not really assigned to a specific realization of the system with like some quench disorder that's just selected from some random distribution. You have to take an average over those realizations of the disorder in order to get something that's a good order parameter, okay? And so what we do is we take many, many copies of the system and we form like a correlation between those copies. If they're all the same, then the replicas are symmetric, and that's not a spin glass. But the miracle is that when you're in the spin glass phase, at least for the SK model, those replicas become different, like very, very different. And so you'll get structure in this overlap function. And then in order to understand that structure, you take an average over everything. Okay? And this basically comes down to those villages in this alpine free energy landscape being non-ergodic. The fact that like noise, technical noise, thermal noise, quantum fluctuations can bring the skier into one village versus another village on each like trajectory of the system when you start from the same initial conditions, mean that replicas can be different. So you start with the same, but you end up with something different. You never get back because you get lost in these deep valleys. All right, that's a little bit weird, but let me show you what this means. So let's say that you've skied into this valley that's alpha or this valley that's beta, and you take an overlap distribution for a given Jij matrix. What you'll see is something that has a structure to this. You'll see like these little peaks that are sparsely populated between plus and minus 1, and then you'll see these big peaks at plus and minus 1. Plus and minus 1 are just that, like if you have a ferromagnet, if they're all up or all down, you get plus 1. If they're like this or like this, you'll get minus 1. But these things show that you have this rugged landscape. If you pick a different disorder realization, and you'll have a different landscape, you pick an alpha and a beta, you'll get something else. And this is a simulation we've done with finite temperature and finite size, so it's a little bit broadened, but you'll get something else. And so what you want to do is average all of that. And so if you do that, then you get the order parameter. So for a paramagnet, which is just constantly fluctuating in time, everything's at 0. A ferromagnet, you just have the two goalposts. but a spin glass will have some averaged content in the middle, and this is the net of the goalpost, the famous Parisi goalpost for the spin glass order parameter, okay? And this is what is evidence for replica symmetry breaking that will give you this, okay? So that's the spin glass order parameter, very weird. So that's the symmetry that's broken. So like an Ising system, like a ferromagnet, the symmetry that's broken is Z2, all up or all down. But the structure is that everything is pointing up. Like a crystal, the symmetry that's broken is translational symmetry. But the structure that emerges is a lattice. So what is the lattice in the spin glass? It's ultrametric correlations between these replica spin configurations. So again, in a traditional system, like, the structure that comes out is this. This is the structure that comes out of the spin glass. And so this is very weird, but this is what Parisi won the Nobel for. And it pops up in all sorts of models of complex systems, is that if you take this Q alpha beta, okay, and then you take 1 minus it, you get something called the distance. So 1 minus the Q alpha beta. And what you find is that naturally these distances between any different alphas and betas obey the strong triangle inequality. So what is that? And you can also represent it like this, sorry. So what is that? So the regular triangle inequality gives you this triangular structure here that, the length of Z has to be less than the sum of the other two sides. The strong triangle inequality forces this to always have at least two sides to be equal, okay? So you get triangles that are restricted to this. And then if you order this, you can form a family tree, okay? You give this a dendrogram that looks like a family tree. And then you can ask yourself in your mind if this is really true, and it is true. And you can represent this like a matrix, like so. So this is the structure that emerges. And so it's really important. People have found that this appears in simulations of turbulence, of ecological systems, analyses of DNA, RNA, protein sequences, computer algorithm, can all spit out some structure that does this, and that's why this was Nobel worthy. But it's never actually, as far as I know, been directly seen in nature. Microscopically go in, read out the spins, form the tree, and be like, yeah, there it is. In fact, people have dealt with this since the 80s so much that they think it exists in nature, directly observed, but I don't think it ever has. And so what we've done is actually see this in nature, have seen this in nature. So how do you do that? How do you see replica symmetry breaking in this kind of structure? Well, you want to microscopically paint this picture, but you can't do that, at least not so far, with STM or AFM or something, because, the spins are too small in this to really read out the 10 to the whatever number of spins. So we've got to use some atomic physics, some quantum simulator, that's Quantum-Optical, to read out all the different spins. So that's what we have done. We've been working on this for a decade or so, and we finally got it to work a few years ago. And let me just briefly tell you how it is, because I can't give a full talk on exactly how the hardware works, but I'll just wave my hands and sketch it. So this is the very colorful sketch of the apparatus. It looks like a bunch of wires and aluminum foil and lasers and stuff, but this is the theorist version. So you have a Fabry-Perot cavity, so you have two mirrors that oppose each other. And not shown are tweezers, optical tweezers, that come from the side that hold little clumps of BECs. Here's 8 of them, but we've done up to 20 of them so far, that are inside, trapped between them. And then what we do is we send in some photons. So this is initially in a vacuum state here. We send in some photons from the side, and those photons will scatter off, say, this clump of atoms into the cavity mode. Okay? That does two things. One, it creates a very tight cavity mode focused exactly at those atoms. Why? Why does it not look like a Gaussian? It's because we're using a weird kind of cavity, a confocal cavity. So something we've developed over the last dozen years is multi-mode cavity QED. A particular case of it is the confocal, where the radius of curvature of the mirrors is equal to the length of the mirrors, and that superimposes thousands of cavity modes, TEM modes, onto the same spot. So you can actually have a local representation of a photon wave packet in a cavity, not a big Gaussian. So you get a supermode here, supermode here, supermode here, supermode here, whatever you want to call it, around each one of the atoms. And then, because it's confocal, when that light hits a mirror, it comes back as its Fourier transform. That's what confocal means. The object plane, the light of the object gets refocused back as the Fourier plane. And that Fourier plane is this big blue thing, and that big blue thing gives us connectivity among all of these different spins, gives you a large field that connects a photon between all of these different spins. And if you work it out, you'll find that the Jij matrix that connects all of these, this little network, looks weird. It's the cosine of the dot product of the distance Ri from the center to one of these, dotted into the center to another one of these, normalized by the waist of the cavity, which will say at 35 microns, and then cosine of that. So if you just change the positions a little bit, you change the argument of this, you can easily go from positive to negative, just like that, okay? Just like very, very quickly change the sign. And so just by changing this a little bit, or just the positions, you can get a random distribution, and that's how we get the spin glass, okay? So
it's not correlated between.
No, it could be uncorrelated. If they're far enough away from each other, so this wraps very rapidly, then it becomes uncorrelated. You get a Wigner-Dyson distribution of this matrix, I can say. So the first thing we did was to make XY spins. And so the light that comes out, we beat it against this pump field to make a hologram, a spatial heterodyne. And you get this twister map, the game Twister. It kind of looks like that. But the color and the intensity of light tells you the amplitude of the spins, but also the color tells you the phase. So in this XY model, you can see that these are pointed in all different directions. So what's going on is that, the light bounces off to another clump, and depending on the phase of that light, it's either a positive or a negative interaction. So, and then we can increase the number, and we can change things a little bit to go from XY spins to Ising spins, and that's what I already showed you. So it turns out that the cooperativity of this is incredibly high. It's more than 100, which is, if not a world record, it's very, very close. And so it's a really great quantum optical system just in general. So let's do the experiment. We can make a ferromagnet with this, and we've done, and all these colors would look the same in a ferromagnet. I don't have time to show you that. So let's just jump straight to the spin glass. So for a given Jij, given arrangements of these atoms, we run the system once, and we go into one of these villages, and that village has this pattern. And then we run it again from the same initial conditions, as good as we can do it, but given some noise in the system, thermal, quantum fluctuations, whatever, the system goes into a different village, and a different village, and a different village. And we can do this 100 times. We do it 100 times. Sometimes you get the same village, but oftentimes you don't. And then you take the overlap of these, and what you get is this two-dimensional, because it's an XY spin, you get this two-dimensional representation of that overlap matrix, where you have the peaks on the side. Those are, the kind of all up or all down kind of things, but you get the structure in the middle. We can project it down so you can make it easy. And you can see that, yeah, this is sort of like what you would simulate for something that was finite size and has a little bit of a finite temperature. And so this is evidence for replica symmetry breaking. And because we have, for the very first time, done this from a microscopic measurement of the spin states, okay, we can go in and we can assign each one of these peaks to a particular replica overlap. This is not something you can do with random laser systems or any other system. What you can't do in any of those other systems is to then go and build up the dendrogram, the family tree, and show that this has kind of nascent ultrametric structure, has this block-like structure. And so I claim that this is the first time that ultrametricity has been directly observed in nature. I think that's a big deal, because it's something that's very, very consistent across all complex systems, this ultrametric structure. Okay, so, and then the last thing I'll show is that you can then average this over the Jijs to get that good order parameter. So this is like a lot of work. This is the overlap matrix for 123 different Jijs, and you average this over, and you get this Parisi distribution. So it looks a lot smoother. Now it has this weird structure. That's because it's a network of finite size, so it's not completely smooth. But as we increase this, as we make a better quantum optical system with more sites, now we have like double the number of sites. We can triple and quadruple that with better tweezer systems. You'll make this more and more smooth. And then, of course, the magnetization is also 0. So that checks out. Okay, so the last thing I'll say is that we did some theory work also with Sarang that shows that if you go to the spin 1/2 limit in the transverse Ising model, you can see replica symmetry breaking of the spin ordering up or down at the same time as one could in principle measure entanglement among the spins. So this is showing that this system with the real time scale, everything is realistic about these simulations. You can get a fully quantum spin glass in the system. And it could do some cool things like, you can pass through energy barriers in a trajectory. It gives you lower energy than in a semi-classical system if you look at the energy versus time. It probably doesn't survive to large system sizes, but it's kind of a neat thing that the quantum system, because of the entanglement, can do. And you can use this system to make fully quantum associative memories. All right, so the last slide is to conclude. This multi-mode cavity QED system that we have, you can use it in many different configurations. It's kind of like an active quantum gas microscope. So if you take like Marcus Greiner's quantum gas microscopes, where you can use a lens and look at a lattice or like a Hubbard model very close, our system is sort of like that because the light that leaks out gives a single site resolvability. But of course, the light gets fed back directly onto the atoms because it's mirrored to give you interactions. And we've used that already to do other cool things like make a lattice that vibrates, so build in phonons into the system. So we actually have an optical lattice that vibrates, that has sound. And you can think about all sorts of fun electron phonon-like physics you can study with that. And this is the team again. In my lab, we have 2 other experiments. We have one-dimensional gases of dysprosium, the most magnetic element. We've used that for topological pumping into many-body scar states, and we recently looked at the nonlinear response of those scar states. And then we have another new cavity experiment, multi-mode cavity experiment, where instead of atoms, we put like TMDs, graphene, Moire materials, and coupled to the excitons in them to do similar physics with the goal of hopefully increasing the superconducting TC with light. We don't know if that'll work, but there'll be a lot of fun things we can do with that. Okay, good? Good, all right. Any questions?
Thanks for a great talk, Ben. We have plenty of time for questions. A reminder to use the microphone or online. I see Jameer's hand, and you're... Actually, maybe Dan is closer to the microphone, and then Jameer after.
Step up to the mic, Dan.
Thanks. Great stuff, Ben, as always. I guess, could you help me draw the connection between the observation of the different sort of spin glass modes that you're talking about, and then are you programming memories into this and reading it out, or are you, for example, how do you feed in a questionable memory and get a more solid recall?
Yeah, I didn't, because of time, I didn't have the slide. I didn't show you the slide of how we do that. If you go back to the picture of the cavity, right? So we pump from the side, we arrange the atoms. What we have now is a spatial light modulator or a digital mirror device coming in longitudinally from the cavity that directly shines a pattern of light through the cavity mirrors. That pattern of light is shaped so that there's a beam that goes to all 16 sites with a certain phase. And that we shine on before we pump the system or as we're pumping the system. So we're seeding the system with a particular pattern. It's like a longitudinal field in the Ising model as we turn up the transverse field of the Ising model. And if that longitudinal field is strong enough, it'll cause the spins to want to orient with respect to this one. So the point is, if we do that with a mistake, does the dynamics of the system, when we pump part of it, correct the mistake in the emitted light? And the answer is yes. And we can do this for several mistakes, and that's that recall curve.
Okay, great.
Is that good?
And then, got it. And then how do you program what memories the system remembers?
Good. So right now we have this nonlinear resource, which is just, and put the atoms in some location. That forms a glassy landscape, which gives us a resource of an exponential number of minima. Then we go and characterize where those minima are in spin configuration space, and we create a dictionary, okay? And so that dictionary is just like, if we want this pattern, then it's closest to this minima, okay? And then we just have that lookup table. So there's some that are exactly and some that are not, and then we can cancel the ones that are not because we have this exponential resource, right? What we can't do right now, I mean, you could do in principle with like arbitrary tweezers, is to go in and place the atoms down and make almost any sort of pattern you want, but not exactly, because you would need n squared degrees of freedom. We have n degrees of freedom. But the point is that because you have an exponential landscape, you're going to be doing well enough to do that. We also see, and this is like kind of, news headline breaking. We also see something that is elastic in the system, which eventually can give us plasticity. So we see that the atoms actually move in their tweezers, I think sort of like what you've seen in your lab. They can move in response to the stimulus, which then actually terraforms this landscape to make it more optimal for recall. We actually see that it makes it more optimal for recall. So that's a really cool thing that we're exploring. Yeah. Did you? Somebody else? Jamir? Okay.
Andrew? Yeah. Thanks for the talk. It happened kind of, there was one slide about quantum effects, and it was kind of fast. I guess
it was
many questions like, are the minima that you end up in effectively classical? And there's some statement that the trajectories that you
I don't want to belabor this point because I don't want anyone to get all excited that you see quantum advantage, because you don't. Like the system probably doesn't, this effect doesn't survive to large system sizes because gaps close. But it is notable that when you have spins that are entangled, when they go through the transverse, when you hit the critical point of this transverse model, with this being a spin glass, you both break Z2 of the icing, you break replica symmetry replica symmetry, and you generate a lot of entanglement transiently until you get a lot of light coming out of the cavity, and that heats because of back action. In this region here, you can go through, if you think about the collective Bloch sphere, because you're entangled, you can kind of go, instead of just the surface of the Bloch sphere, you can go through the center of the Bloch sphere. The center of the Bloch sphere allows you to go around energy forbidden peaks that a semi-classical spin configuration would have to go over. So if you look, this y-axis is a factor of 10 different. Because you have an entangled system, you can go straight through that and get to lower energy states because you can kind of go around these barriers rather than have to hump it over. I don't think this effect will persist to large system size, but it does in these smaller systems. Does that answer your question?
It does, yeah. I mean, this is exactly where I was getting to. Can it live when it gets, can quantum effects survive when it gets bigger?
I think you'll have quantum effects. It's just whether those quantum effects give you some energy minimization that's more effective. I would doubt it, but yeah. I mean, we'll try. Like, we already have a system size that's double. And like once we go to the spin 1/2 limit, which we're working on experimentally, we can just see it experimentally what happens.
Hi Ben. So was looking forward some opportunities in cavity QED to go beyond all-to-all. So for instance, could you start to see some deviations from all-to-all, like with some tails and access regimes where spin glasses are not known? Or equivalently, could you in 5-7 years combine efforts with Monica and benefit of these programmable interactions with disorder to go into really, I don't know, short-range spin glasses, stuff like that nobody understands?
Yeah, okay. Monica's in the back there. Yeah, always willing to hang out with Monica down the building over. So the Sherrington-Kirkpatrick model was a great place for us to start because there are a lot of results that we can compare to, like you can do RSB calculations and compare it, which we've done. And we see some interesting effects that are intrinsic to our driven dissipative system. So it's a great place to start. But you're right that, if you want to ask questions of unknown physics in equilibrium spin glasses, cutting some of those links is the right thing to do to get down, to the question of, what is the order in 3 dimensions? I think we know how to do that by crafting the multimode cavity in a particular way. We will try to do that in the future. So I think the answer is yes. The way that Monica, or maybe Hellman has talked about, but Monica's realized, that's a kind of related but different direction of doing that. I think you can add that in. You could maybe add that in. I think the difficulty there is getting enough random sign changing interactions, but Monica figures out everything, so she'll probably figure out how to do that at some point. So I think in the future we can go. I think what's neat about this system is that, it's SK and people in principle know a lot about that, But this is a different type of spin glass, folks. Like a spin glass in equilibrium is naturally metastable, like it's non-equilibrium because it's slowly in log time going through these metastable states. That should be true here, but wrapped around that, we have another source of non-equilibrium because this is driven and dissipative. We're putting photons in and photons coming out. So in some sense, it's doubly non-equilibrium. And I don't think anyone's really explored that. So like folks in this audience, I would encourage you to help me figure that out. Like what does that do to the long time aging dynamics of the system? Let's try to simulate that.
Cool. This is more a theory question maybe than an experimental one, but in early days people have said that the capacity of a quantum associated memory would be way larger than a classical one, even exponentially. You have an opinion on this, or could you see something to check on this?
Okay, so yeah, so the quantum-optical associated memory, we had a paper from a few years ago, theory paper with Strang, that shows that, you know, not a really quantum associated memory, but a quantum-optical, because it's driven and dissipative, gives you an exponential capacity alone. So I agree that that is true. The next step would be like, what more do you win by having the spins to be spin 1/2 and entangled? There, I could imagine you have a large capacity, but I've actually read different definitions of what a quantum associated memory actually is. There's different ways you can think about it being quantum. And I don't know if there's a difference among those in terms of capacity. So I believe it. I just don't know specifically what it means for a given case.
Thanks.
Yeah.
Sebastian?
Yeah, maybe alternatively to these beautiful replica symmetry breaking diagnostics of a spin glass, you could also look at the dynamics, really. So, or basically fluctuation versus responses. That, I mean, is there anything dynamical that you have already done? Or
yeah, we're starting to do dynamic susceptibility experiments. We've done like 2-point correlations a little bit. We haven't written this up for publication. We've got to do a lot more on this. But yeah, because of that DMD, we can go in, and this is different than any other spin glass system in the world. We can really go in and flip one spin and see how all the other spins respond to that. And of course, you know, with the arrested dynamics of spin glass, it should take a while for it to heal. But you know, no one's ever seen that because you just usually take this thing, put it in a big Tesla magnet and something. You can't go and like flip one spin. Or you can flip 2 spins or 3 spins, you know, and do correlation measurements and look at it at a time. So we plan on doing all of that stuff. We want to overhaul and improve the system a little bit more. But then, yeah, that's something we can do. Thanks.
One more question. Maybe I will ask a question.
Uh-oh.
So you, friendly one.
All right.
You kept mentioning the driven dissipative aspect as being important, but specifically with the dissipation.
Yeah.
So the dissipation is, you know, it's correlated loss, right?
Yeah.
There's maybe randomness there. Does that change the story, playing a central role? In giving the talk, you stressed the Hamiltonian and the random JIJs, but there's randomness in those collective dissipators.
Exactly. So I didn't. So we have thought about this a lot. You know, Strang and Jonathan Keeling, who I collaborate with. You know, so that dissipation gives you this kind of fall off of the entanglements, and you can kind of go back and work out exactly how that works. It also is a thing that gives you. Okay, so there's another slide that I could show you, a result from another paper, PRX in 21, that dissipation is what gives you this exponential capacity because it gives you larger basins than just like Glauber dynamics. And what we see, at least in principle, is that you get steepest descent dynamics in a physical system naturally because the light that comes out of the cavity after having scattered it off the atoms is a little bit higher energy than the lower one, and it turns out that the spin that can flip is a spin that gives you the largest energy difference. And so you can realize with driven dissipative dynamics, steepest descent dynamics or navigation of the landscape, which is not something that is very efficient in this computer here, but seems to be very efficient here. Numerically, this should come in at system size 30 size, We're at 16. We've kind of done 20. So we're not too far away from being able to see that effect. That would be pretty neat, I think. Yeah.
Well, I think this is a good time to thank both speakers and to break for coffee.